Hi, Mick McQuaid here again for the second time on day 11 of iste780 data-driven knowledge discovery. In this recording, I'm going to talk a little bit about the shrinkage methods, which are ridge regression and the Lasso, and they share the use of a tuning parameter, and so we'll talk a little bit about the tuning parameter as well. There's a little bit of stuff that we're going to skip here, the Bayesian interpretation stuff. So let's get started here. So shrinkage methods. So previously we just talked about subsetting methods that take a subset of predictors, and we find some way of choosing among that subset to find the best model. Another thing that we can do is shrink the coefficient estimates or regularize the coefficient estimates towards zero. And this turns out to be a good idea because it can reduce their variance. So, and there are two techniques for this, ridge regression and the Lasso. And they're a little bit different in that ridge regression uses all of the P predictors, whereas the Lasso assumes that some of the P predictors equal zero. And so they're useful in different situations. Ridge regression is very similar to least squares. It's advantageous to use if you know how to pick the tuning parameter, which we've already actually learned. We're just going to review the technique that we're going to use to pick the tuning parameter, believe it or not. So here is how we pick the predictors in least squares. We want to minimize this quantity, RSS. And in ridge regression, we want to minimize this quantity, RSS, plus lambda, this tuning parameter, times this parameter, this sum of the squared coefficients. And so if lambda equals 0, then this is the same as this. So in other words, if lambda equals 0, ridge regression is equivalent to least squares. And ridge regression differs more and more from least squares the larger you make the lambda parameter. So a great deal of this is choosing the size of the lambda parameter. Now, this idea of summing the squared values as a penalty, summing the squared values of the coefficients as a penalty, has the effect of shrinking them towards zero. So we want to minimize RSS subject to that we're trying some penalty function on the size of the coefficients. So obviously if some are 0 or are close to 0, that reduces the penalty. And if we can reduce that with lambda large, so much the better. And here's an example of increasing lambda and the effect that it has on the coefficients for the credit data set. So see, it's shrinking the coefficient. As lambda gets larger, the coefficients get smaller for the most part. Now this over here is a bit more of a difficult diagram to read. This should be read back to front. So this goes from 0 to 1, but this term actually goes from 1 to 0. So if lambda is 0, so if on this side of this panel of the diagram, if we're way over here, that means we're way over here in this one. So this term is 1. It's in fact, this and this are equal if we're using least squares, that is, if lambda is 0. This dwindles to nothing, though. These become nothing if lambda is infinite. If lambda is infinite, this dwindles away. So a little bit difficult to understand. I think it's not very intuitive, and it requires some linear algebra. So this is the L2 norm of a vector, and the definition is given here, but the mechanics of it aren't provided in this textbook. So this is something that we can just sort of um, use, so we can think of the x-axis as the amount that the ridge regression coefficient estimates have been shrunk towards zero. A small value indicates they've been shrunk very close to zero by increasing lambda. Okay, now we generally want to do ridge regression after we standardize the predictors. If we standardizing the predictors, this is an important term, even though we're not going to really do anything with it except using R. We'll call upon R to standardize the predictors. We need to do that to make them all on the same scale, and I can think of a good example of this to clarify what we mean by this, which is height and weight. So suppose that you're evaluating persons on the basis of height and weight. This is something that can be done, for example, with athletes. And so let's say the average height of a bunch of athletes is around 72 inches, and their maximum height is around 80 inches. And their weights are around 200 pounds on average, and the maximum weight is, let's say, 350 pounds. I'm, of course, thinking of NFL, NFL draft pick football players. So if we think about combining their height and weight, which we will in the next recording, if we think about using both of those, it's difficult to reconcile the fact that the average for height is around 200, and the maximum of it is did I say 200? The maximum for height, the average for height is around 70, and the maximum is around 80. Whereas the average for weight is over 200 and the maximum is over 300. So those numbers just don't fit well together. So if we could standardize them so that they're all on the same scale, so that everybody has a mean of 0 and a variance of 1, that's going to simplify figuring out which of these is more important. We'll be able to tell which one has the greatest inherent variability by standardizing, rather than the greatest nominal variability, which is what we get when we use different units. And I should point out that another way we can deal with the height and weight thing is to use different units. Instead of inches and pounds, we can use centimeters, or we could use millimeters and grams or something like that, and maybe we can make the units solve the problem for us. But the simplest thing to do is just to standardize. So that's what we do. Now, ridge regression in general is superior to least squares because of the way it handles the bias-variance trade-off. So if you start out with a lot of variance, the fact that ridge regression reduces variance quite drastically, and you can see it in this picture as we grow lambda, this is the variance is being reduced at the expense of a little bit of bias increase. So where we get to the minimizing of the mean squared error is at a place of very low variance and of relatively little bias. And then this again is the L2 norm of ridge regression divided by the L2 norm of least squares, and it's read the opposite way that the other one is. So this is when lambda is 0, and this is when lambda is infinity. Okay, so so this is generally a good deal if you can come up with a good tuning parameter and you have a lot of variance. Another thing that makes ridge regression good is if you have a lot of predictors, all of which are important. And you never know that in advance, so you don't know whether ridge regression is going to be useful in advance. That's a big limitation. of all the techniques. You don't know which one is going to turn out to be right. But these are the circumstances under which ridge regression works best. Yeah, if the least squares estimates have high variance, that is a strong indicator for ridge regression. Okay, there is one problem with ridge regression that is that it will include all p predictors in the final model. So it would be nice to have a technique that doesn't necessarily do that. And the lasso is very similar in some ways to ridge regression, but it's very different in another way. And the difference, if you look at the model, they look identical, except that here we're looking at the absolute, the sum of the absolute values. And this changes the shape of the lasso's region of restriction, restricting the coefficients such that some of the coefficients will certainly be zero. So the lasso is superior to ridge regression in situations where you have quite a different where you have some predictors that you know are really irrelevant or that you suspect to be really irrelevant. Again, that's difficult to know a priori. But the lasso, here, there's an example here. This is the credit data. So here's the, so these are the lasso coefficients as a function of lambda and as a function of, this is called the L1 norm. And this is just an alternative formulation so that you can see that it's, by the way, that it's minimizing some quantity subject to that these two quantities are, so this is lasso and this is ridge regression, are less than some threshold. Oh yeah, here, so this is a really good picture that shows the difference between the lasso and ridge regression. So this is the lasso on this side, and this is ridge regression. And here's the optimal coefficients, and this, you can read this like a contour map where every value in the along the red ellipses is equal to every other value along that same red ellipse. So as we grow here to meet these constraints, the fact that this is square means that we're likely to meet it at a place where one of the coefficients is zero. So in this case, we have two coefficients, and here is a situation where a coefficient is zero, and here's a situation where the other coefficient is zero. And we're very likely to meet it at one of those places. And that's because we're using the absolute value function on the betas. And here, the function, the square function, is giving us a circular region. So there's no particular point along this region that's any more likely than any other. So it's, in this particular case, we have beta 1 is very small, but it's not zero. So so that's a big difference between the lasso and ridge regression. The lasso is going to explicitly make some zero and explicitly make some, let me find, there's an example here. So here's an example where the lasso does a better job. And this is our old friend, the cooked data set. And this particular data set is chosen specifically so that only 2 of 45 predictors. By the way, that's another really great thing about the lasso and ridge regression, is that they can handle a large value of p. But in this particular case, only 2 of the 45 predictors are relevant in the model. And so we see there's another picture of this same situation here. It's quite a ways away. Here it is. This is the same model with the coefficients plotted against the L1 norm. And these all are the ones that turned out to be irrelevant. These are the two that turn out to be of relevance. Okay, and then here's another picture of the difference between the lasso and least squares. And what you see here is that the if we are looking at the coefficient estimates plotted against the values of y, ridge regression gradually reduces all of the coefficient estimates, whereas Lasso suddenly drops to 0 and then doesn't do anything for a while and then drops further. So they call this soft thresholding. Okay, so anyway, and as I said, I'm going to skip the Bayesian interpretation. In general, I'm always going to skip any section that has this steep grade symbol beside it, partly because this is a summer course. There's no way I can tell whether these sections are going to be easy for you guys or not. I mean, I just don't have contact, you know, the contact is all kind of one way here with these video lectures, so it makes it difficult to know what to focus on. Okay, but here's something that we certainly want to focus on, and luckily we've already figured out how to do it, which is selecting the tuning parameter. So these are both really good techniques, and in the case of the lasso, it's a relatively new technique, relatively recently promulgated technique, and so they're worth doing if you can figure out the tuning parameters. And so luckily cross-validation works out pretty well to find the tuning parameters. Here's an example of cross-validation on the credit data that is used prominently throughout this. So here's the value of lambda that's chosen by, and this is k-fold cross-validation with k equals 10. And I believe there's another picture of the same. No, I guess there's not. Okay, that's the only picture of it. So this is a picture of k-fold cross-validation. Here's where it chose a value of lambda, and notice that and this is in the credit data. This is not that Cook data set that I was just mentioning. So here are the coefficient estimates. And I'm not clear on what, I think these are irrelevant estimates. Yeah, these are all estimates chosen to be irrelevant, plotted as a function of lambda and showing the value of lambda that cross-validation came out with. Okay, so that's about it for shrinkage methods. So they're different from the subset selection methods in that we might end up with all of the values, albeit very small, certainly in the case of ridge regression. The lasso is kind of like subset selection in a sense, but its formulation is very much more like ridge regression, and the results are very similar in a lot of ways to ridge regression, although they're different in the sense that's shown in this picture and in the picture with the square and the circle. Different in these senses. Okay, so in the sense that the lasso is likely to drop some, so it is a subsetting technique, whereas ridge regression drops some, but doesn't drop them to 0 necessarily. It's no more likely to drop them to 0 than to any other small value. And then I should mention that they're both computationally preferable to the subset methods. So if you can pick the right lambda, you only have to do ridge regression once. So that's an extreme computational savings if you have a very large model, which is where these find a lot of use. Large models with high variance. All right, thank you very much for your attention, and I will talk to you next about dimension reduction.